Hi everyone, hope you're all doing well. Now time for today's lesson where we're going to be looking at capacitors. So learning intentions for today to explore capacitor circuits. There's a lot to get through, so you're going to need to bear with me on this one. I can define success criteria. I can define the relationship between charge and potential difference in capacitor circuits and use this relationship to solve problems. I can define a relationship for energy in a capacitor circuit. I can identify charging and discharging curves for a capacitor in a capacitor circuit. So the capacitor, this is the symbol for a capacitor. This is a component, a symbol for the component called a capacitor. The capacitor is a very useful device. So capacitance, first of all, tells us just how well a component can hold charge, or how much charge, essentially, a component is able to hold. So that leads us on to a capacitor. A capacitor, therefore, becomes a component which can store charge. Capacitance is measured in these units here called farads, and we use the capital F to as the abbreviation for that one. So let's come back to our symbol here. We're going to have a little look at this in a little bit more detail. So if we move that to the side and then just bring in a bigger picture here. What we've got, if we hook one side here up to the negative terminal of a DC power supply, and then the other side here, if we hook this up to the positive terminal of a DC power supply, then what happens is we can send charges along here. Now what we basically got here, our capacitor is basically, in the most simplest form, just two parallel plates with some sort of gap in the middle, some sort of insulator between those two plates, something that's going to stop those charges from being able to travel from one plate to the other. You can do that just simply by having two plates with some air between them, presuming you don't have a charge that's too high. But essentially that in its most basic form is what a capacitor is. So if we hook this up to the negative terminal of a DC power supply, then what happens is we've got an electron that's going to come in from here and it's going to travel along to this plate, but of course it can't go anywhere once it's reached the plate, so it gets stored on that plate. So that little charge, that little negative electron, gets stored on this plate, as we can see up here. Now of course this side here is connected to the positive terminal, so what's going to happen at the same time, we're going to have a little negative electron is going to get pushed away from this plate and travel towards the positive terminal. And essentially what we end up with is the equivalent of a positive charge here. So we've got an atom that's going to be missing an electron, so it's going to have an overall positive charge. So we've got now got a positive charge on this plate and we've got a negative charge on this plate. And that's going to continue happening. We're going to have another negative electron travels in, it's going to be stored on that plate, and then we're going to have another electron leaving the opposite plate and travelling towards the positive terminal, giving us another negative charge here and another positive charge here. And that's just going to continue. We're going to build up a charge, negative charge on one plate, and we're going to build up a positive charge on the other. That can be incredibly useful. So let's just have a look at charge versus potential difference. So let's consider the circuit that we're looking at here. So what we can do with this circuit here is we can switch this switch to position A, and what happens is we will charge up our capacitor. So the electrons are going to flow from the negative terminal to the capacitor, and they're going to be stored on this plate of the capacitor, this side of the capacitor, and on this side of the capacitor we're going to have the electrons flowing off that plate and round towards our positive terminal. So we end up with our positive charges stored on this side and our negative charges stored on the other side. Now once the capacitor is fully charged, what we can do is we can switch this switch here from position A to position B. And then what happens is our capacitor is going to discharge. So it's going to discharge through the coulomb meter here, and it's going to use up all the energy that is stored travelling through this resistor. And we can continue that cycle. We can charge it up, we can we can discharge it. Now, if there's an ideal world and we were able to do some experiments, we could do an experiment. We could hook this up to a variable DC power supply. We could try different potential differences here to charge up a capacitor and see how much charge it's able to store. We could go ahead and plot ourselves a graph and we'd get something which looks a little bit like this. So on our x-axis here we've got potential difference, on our y-axis we've got charge, and what we would find is, presuming our results were really good, we would find that we've got this relationship here, and this is a directly proportional relationship. So it travels, it's got a straight line, and it's going to go through the origin. Now that's very useful because if you remember back to maths, if you've got your equation for a straight line, then we could derive maybe some sort of equation from that. So let's just bring up our equation for a straight line. So remember your equation for a straight line, y equals mx plus c. Now what do we know about this? So we know that y is q, because that's just the y-axis. We know that x is v, because that is the x-axis. We know that c is just with the y-intercept, so that's what it's going to cross the y-axis, and that's going to cross the y-axis at 0 because it's directly proportional. So let's plug those in and we get q equals mv plus 0. So obviously we can ignore that 0 at the end. So that's just leaving us with q equals mv. So m is going to be some sort of constant in this case. So m is just this constant value here. This is the gradient of this graph. Gradient obviously is a constant value. So if you pick any value of q and v and you do q divided by v, you're going to get the same number as if you pick any other two corresponding values of q and v. And this value for this gradient here, this constant, is what we call capacitance. So this is the capacitance of our capacitor. It is basically given by the gradient of this line here. So let's have a look at that equation. We have our equation here. Q is equal to CV. So that is Q standing for charge, measured in coulombs, C being our capacitance, measured in farads, and V being our potential difference, measured in volts. So let's have a look at a worked example, just to complete this part of the lesson. A capacitor is connected to a DC power supply. When fully charged, the potential difference across the capacitor is 5.9 volts, and the charge stored is 32 microcoulombs. Calculate the capacitance of the capacitor. So I hope you're all going to be with me here on this one. First thing that we're always going to do is we're always going to write down our shopping list. So shopping list comes first. So let's plug in these numbers here, just lifted straight from the example. V being our potential difference is 5.9 volts. Q being our charge was 32 microcoulombs, and C, our capacitance, is what we're looking to calculate. Now I'm hoping you have noticed already that we're going to have to do a little conversion here. We're going to have to convert Q into coulombs. So 32 microcoulombs becomes 32 times 10 to the minus 6 coulombs. You can also divide by a million, but I prefer to do it this way. So for our first mark, we're going to write down our equation. Q equals CV. Then we're going to substitute in our values. That gives us our second answer, second mark there. So 32 times 10 to the minus 6 is equal to C times 5.9. Need to rearrange, obviously. That gives us C equals 32 times 10 to the minus 6 divided by 5.9, which gives us an answer of 5.4 times 10 to the minus 6 farads. Obviously make sure you round that off correctly when you're doing your calculations. Just to remind you, we've got 5.9 volts here, we've got 32, so that's two significant figures. We want our final answer here to be to two significant figures. So just a little reminder, first mark there for our equation, second mark for writing in our values, substituting our numbers, and your final mark for the answer with the correct units. Okay, so energy is stored in a capacitor. So if we're putting all this charge on a capacitor, we're obviously going to be storing some sort of energy there. Let's have a look at this circuit here. Now, what we've got here, we've got our negative terminal of our cell, and it's going to be sending out electrons along here and trying to store charge on here. Now, as we build up charge on here, it's going to become more difficult for other charges to want to go to the plate. Basically, like charges repel, so if you've got another electron and it's going towards that plate, the charges that are already stored on that plate are going to repel it. So if you want that electron to get to that plate, you need to make sure you're putting in enough energy, and that energy is provided by our power source, or our electricity source, our cell in this circuit here. So basically what we end up with is a bunch of electrical energy stored in the charged capacitor. Very useful. It means we can then use that to do something useful. So if we bring back our graph that we saw just from a couple of slides ago, so this is again charge on the y-axis, potential difference on the x-axis. Remember, it's just a directly proportional relationship here, so it's going through a straight line going through the origin. If we want to calculate that energy, what we can do is we can just calculate the area under this graph here. So the energy stored in a capacitor is just given by the area under the charge potential difference graph. So the area under the graph is this bit marked with red here, and obviously this is just a triangle. Area of a triangle is just a half of the base times the height, so that's going to give us the area under the graph being a half of Q times V. So let's have a look at that equation just to make sure we've got that down properly. Our equation then becomes E of course being the energy stored in the capacitor in joules, is equal to a half times Q, which is the charge in coulombs, times the potential difference in volts. Now we could leave it there, but we don't like to do things by halves. We have another equation that we've just thrown at you just a few minutes ago, which links Q and V together. So what we can do is we can plug in some of those equations, rearrange them a wee bit, and we can come out with this equation here, E equals a half CV squared. We can also come out with this equation here, E is equal to a half Q squared divided by C. C obviously still our capacitance, Q still our charge, V is our potential difference, and E is the energy stored in the capacitor. Now I'm not going to bother showing you which of these are which. I'll let you fill in the blanks, which is energy, which is potential difference, which is charge. I'll let you fill that in when you're doing your own notes. So, second worked example time. A 40 microfarad capacitor is fully charged using a 50 volt supply. Calculate the energy stored in the capacitor. Once again, we're going to start off with a shopping list. So, plug in our numbers here. We've got our capacitance was 40 microfarads, which is 40 times 10 to the minus 6 farads. Our potential difference was 50 volts, and of course we're looking to find the energy stored in the capacitor. So first thing we're going to do is write down the appropriate equation. That's E equals a half CV squared in this case, because we've got C and we've got V here. I'm going to plug in our numbers. So E is equal to half times 40 times 10 to the minus 6 times 50 squared. And then we can answer that. It comes out at E is equal to 0.05 joules. That was an exact number, I should say there, so we don't need to worry about rounding here. This is just giving us that as an exact number. So, little reminder, where do we get our marks? Well, one for the equation, one for the substitution, and one for your final answer with the correct units. Now, last bit that we're going to get through just now, charging a capacitor. And we have a little look at this circuit here. So again, we've got a cell here, which is going to charge our circuit up. This time we've got a resistor here, and we've got our capacitor here. Now, obviously, what's going to happen here is we are going to be sending charges around this circuit here to store them on the capacitor, on this plate of the capacitor, and then we're going to have negative charges, the electrons, leaving this plate and coming round back to our positive terminal of our cell. So if we were to put in an ammeter into this circuit, what would the current look like over time? How would that current vary with time as this capacitor charged up? Well, it turns out this is what we see here. We see something which looks a little bit like this. To start off with, we have a high current, and current is at its highest at the start because there's no opposition to, remember, the current is just that flow of charge. So there's no opposition to that flow of charge at the minute because there's no charges stored on there. So we start off with no opposition to the charge, so it's able to flow freely. But then as that charge builds up, remember we've said already, it's going to start getting a little bit of resistance. It's going to, the charges are going to be repelled by the charges that are already stored on this plate here. And that's going to cause it to slow down, and that's why we see this curve here, this curve which looks a little bit like this. So as the capacitor charges, the amount of charge that's stored on the plate is slowing down, and the current kind of decreases as you see in that graph there. Now, what we're to look at the potential difference across the capacitor. Now, if we look at the potential difference across the capacitor, we see something which looks a little bit like this. So initially, of course, there's no potential difference across there because there's no charge stored on our capacitor. So it starts off at 0, and very quickly it starts building up, and we see this curve which works its way up gradually until it becomes this constant value here. And this constant value that it reaches is just the supply voltage, so it's whatever this little cell is providing here. So if this cell is providing 1.5 volts, then this supply voltage here is 1.5 volts, and that's the maximum potential difference that we're going to get across the capacitor. If this was a 6 volt cell, then it would get up to 6 volts here and it wouldn't go any higher. That would be the maximum potential difference we're going to get across our capacitor. Discharging the capacitor. Now, we see something similar. I'm going to show you a slightly different circuit. Remember back to one of the slides towards the start, we had this one here. We had a capacitor charged up here when this was switched to A. So we have our charges building up on, the negative charges building up on this plate here, and the negative charges leaving here, leaving positive here, and we end up with our charges built up on both plates here. Now once this is fully charged, we can switch this to B. Now what happens here at this point in time, instead of the flow of electrons trying to flow up this way, we have the electrons here. They can't pass that barrier, we've still got that barrier there, so they have to flow in the opposite direction. So what we actually see is a curve which looks like this. We get a negative current. So the current starts off negative, starts off high as well, because all those electrons are trying to push each other away as quick as they can from here, and as they start to leave, the repulsion from that plate is going to decrease, and we start to see this curve which looks a little bit like this. So we have this curve in the current, and the rate of the current slows down as we approach 0 here. So as the charge starts to approach 0. Now, once again, if we look at our potential difference across the capacitor, in this case it looks a little bit like this. We start off here with a value for our potential difference, which is just going to be equal to our supply voltage. So this is whatever we charge. Our supply voltage was providing. So if this was providing 6 volts, then we would start off with 6 volts here, and we're going to see this gradual decrease, which looks a little bit like this here. Simple as that. So I'm going to leave it at that. Now time for you to have some practice. So I want you to have a look at the electricity question booklet. Go to exercise 4, which starts on roughly page 17 in the PDF document if you're looking at it on Google Classroom. I want you to try as many of the questions as you possibly can in there. Remember to check your answers. The answers are at the back of that booklet as well. So if you don't have them in the back of the booklet you've got at home, you can go onto the one in Google Classroom and you can check your answers in there. And if you're struggling with any of these questions, put your question in the comment. You can send me an email, ask for help. I'm going to be sitting monitoring these comments throughout this double period just now. So finally then, just to wrap up, let's have a look at our success criteria again. Hopefully we can tick all of these off. If we can't, remember, go back, watch the video again, or you can ask for questions and ask your questions in the comments, or ask questions via email. So success criteria: I can define the relationship between charge and potential difference in capacitor circuits and use this to solve problems. I can define a relationship for energy in a capacitor circuit. I can identify charging and discharging curves for a capacitor in a capacitor circuit. And that's us. Okay, so as I say, go have a try at those problems, see how you get on with them. If you're struggling with any of them, ask for help. Depending on what the problem is, I may do a short video, I may do a picture just with a worked solution. I may just type a solution into the comments as a response. We'll see kind of what problem you come up against. I'm more than happy to try and help you however I possibly can. In the meantime, best of luck, and hopefully we'll get to see each other soon.